In this video, we are going to review how to model the path of an object using parametric equations. Note that this is just a review and is not intended to be a standalone lesson. As such, the video may move quickly and may not cover in great detail every piece that we are discussing. For a more in-depth explanation as to why this works, please access the videos from the Parametrics unit. Let's begin. The first thing we want to remember is the general structure of a parametric equation. That is, an x of t equation and a y of t equation. The x of t equation will represent the horizontal distance away from the starting point of the golf ball after t seconds. The y of t equation will represent the vertical distance above the hole of the golf ball. Again, with respect to the parameter t, which is going to be seconds. Now, the structure of each individual equation is actually fairly straightforward, since we are neglecting air resistance and friction. The x equation is merely a classic case of distance equals rate times time. If you travel 50 miles an hour for 2 hours, you've traveled 100 miles. And the y equation is okay to deal with as well. This will simply be an implementation of our vertical motion model that we discussed in our function unit, in our derivative unit, and in our integration unit. With these ideas, we have enough to begin. Let's start by making a list of known information. One thing we know is the location of the tee, or rather the starting position of the golf ball, as well as the position of the hole. The important pieces to note are that the starting x position of the ball is 0, and the y position of the hole is 0. This tells us that at time 0, our x position is 0, and it tells us at time 0, our y position is 12, so we know our starting height, h naught, is equal to 12. The other information that we're going to start off knowing, the other given information, is going to be the initial velocity with which we hit the ball, called v naught, and also the angle with which we hit the ball, which we will call theta. With these three pieces of information, we have enough to figure out everything that we need. Now, before we start actually writing our equations, we need to recognize that the initial velocity is being directed at an angle, which means that the full force of the hit is being broken up into a horizontal component and a vertical component. Using basic right triangle trigonometry, we can figure out what the value of each component is. As with any right triangle, the vertical component will always be the value of the hypotenuse multiplied by the sine of the angle. And similarly, the horizontal component of the triangle will be the hypotenuse of the triangle multiplied by the cosine of the angle. And with that, we have two values that we can use. And so we have v naught x, the horizontal component of the initial velocity, which is v naught times the cosine of theta, and we have v naught y, the vertical component of the initial velocity, which is v naught times the sine of theta. And with this, we have enough information to write the horizontal position, x of t, which we said was just distance equals rate times time, where our rate is simply the horizontal component of that initial velocity, v naught x. So we get x of t equals v naught times the cosine of theta times time. And so now we just need to remember the vertical motion model that we have learned about before, namely, y of t equals negative 16 t squared plus v naught y, the vertical component of the initial velocity, times time, plus the starting height, h naught. And so for our problem, as long as we know the initial velocity, the angle of the hit, and the initial height, we have our model. And with that, we have our model for projectile motion. It's now your task to use this model in the remaining problems. Good luck.